Welcome to College Algebra, Topic 3.1, Linear Functions and Models. Objective 1 is to determine if a linear model is exact or approximate. A model is a diagram, a graph, an equation, a verbal expression, or some other form of communication that is based on observed data. The model should explain present phenomena and should also be able to make predictions about data or results. Some examples of where we use models are business trends, car designs, weather, highway traffic, etc. Most mathematical models are not exact representations of data. Data may appear to be nearly linear, but not exactly linear. A linear model may be used to provide an approximate model of the data. Our example: determine whether f models the data exactly or approximately. Well, if they give us a formula function f and they give us data, the way you tell if it's exact or not is you take the x value and you plug it into the function and see if it gives you an answer. So if x is 1, we get f of 1 is equal to 3.5 times 1 minus 5.5, which is 3.5 minus 5.5, which gives us negative 2. That one worked out exactly. We need to do this for every point in our table. So if x is 2, we would get 3.5 times 2 minus 5.5, which is 7 minus 5.5, which is 1.5. Again, that is true. The next value in our table, f of 3, is 3.5 times 3 minus 5.5. Well, 3.5 times 3 is 10.5 minus 5.5, which gives us 5. Again, that holds true. And then the last one, f of 4, equals 3.5 times 4 minus 5.5. So that would give us 14 minus 5.5, which is 8.5. Because all of the data in the table matches that function exactly, then we say that this is an exact fit. Example 2. Determine whether f models the data exactly or approximately. Again, we're going to take each x value in the table and plug it into our formula. So it'd be 13.3 times 1 minus 6.1, which is 13.3 minus 6.1, which gives us 7.2. That one checks. So for our second point, we plug in x is 2, which gives us 20.5. Again, that one holds true. Now let's do the third one. f of 5 is 13.3 times 5 minus 6.1. Well, we might need a calculator for that one, which gives us 60.4. Far so good. And then the last one, we're plugging in x is 10. So we get 13.3 times 10 minus 6.1, which gives us 126.9. So again, f of 10 is 126.9. So this is also an exact fit. Recall that a linear function is a function of the form f of x equals ax plus b. The graph is non-vertical. There is usually one x-intercept and one y-intercept, except if m is 0, and then there is no x-intercept. For these functions, a is the slope and b is the y-intercept, but remember, normally we call slope m, so sometimes we may talk about m is the slope as well. A constant function is a linear function whose slope is 0. The graph of a constant function is a horizontal line, and there is no x-intercept and only one y-intercept. Let's do an example. Given the graph, find the slope, the y-intercept, and the x-intercept, and then write the formula for f. Well, looking at our picture, we need to pull off some of the points. This is your y-intercept because it crosses the y-axis at 1, so that would be the ordered pair 0, 1. This is your x-intercept, which would be 1/2, so it's 1/2, 0. This is another pretty point. It's not an intercept, but I'm going to use that because that is over 1, down 1. So when we're looking for the slope, we need y2 minus y1 divided by x2 minus x1, and it's usually easier to plug in the whole numbers and the integers rather than the fractions. So if we let this be our first point x1, y1, and this be our second point x2, y2, we would get -1 minus 1 divided by 1 minus 0, which would give us -2 over 1, so our slope would be -2. The x-intercept, we said, is where the line crosses the x-axis, which was the ordered pair 1/2, 0. The y-intercept is where the graph crosses the y-axis, which we said was the ordered pair 0, 1. To write the formula for f, remember f of x is equal to mx plus b, or ax plus b. So we know the slope is -2, so we would get -2x plus the y-intercept. The y-intercept was 1, so our function is going to be f of x equals -2x plus 1. As a review, if you know the slope and the y-intercept of a line, then you can use the slope-intercept form to write the equation of a line. That is y equals mx plus b. If you know the slope and a point on the line that is not the y-intercept, then you need to use the point-slope form of a line. The point-slope form is y minus y1 equals m times x minus x1. In this book, they go ahead and solve for y equals. So what they do is they add y1 to both sides, which gives us y equals m times x minus x1 plus y1. Let's do an example. Write a formula for a linear function f that models the data exactly. Then graph. Well, to write the function, we need two things. We need the slope and we need the y-intercept. So the slope is found by doing y2 minus y1 divided by x2 minus x1. We can pick any two. I'm just going to go ahead and pick these two because they tell us that it models exactly. So we are going to set this up as x from the first point, y from the first point, x from the second point, y from the second point. So when we plug it in our formula, we would get 10 minus 6 in the numerator divided by 2 minus 0 in the denominator, which is 4 divided by 2, so our slope is 2. Now for the y-intercept, remember that the y-intercept is the point where the line crosses the y-axis, and any point on this y-axis has an x value of 0. So if you look in your chart, this point, or this ordered pair, has an x value of 0, which means that the y-intercept is going to be 6. So once we know the slope and the y-intercept, then our function is going to be f of x equals 2x plus 6. Now to graph that, we could just go in and graph each of the points that they give us, or we could go about it and say, okay, if the y-intercept is 6, that means it crosses the y-axis at 6. A slope of 2, remember, means rise over run, so we could rewrite 2 as 2 over 1, which means every time we rise 2, we run 1. We rise 2, we run 1. Or if we go down 2, we go back 1. And if you'll notice, these are exactly the same points as they give us in the table. The next example. Write a formula for a linear function f that models the data exactly. Then graph. Same thing, to write the equation of a function, we need the slope, whether we call it m or a, so we can just pick any 2 points. So I'm going to pick x1, y1, x2, y2. plug it in our slope formula, y2 minus y1 divided by x2 minus x1. So we would get 32 minus 30 in the numerator, 20 minus 15 in the denominator, which gives us a slope of 2/5. Now in this case, they don't give us the y-intercept. So one way to do would be to look at the graph and see if we can get a pattern. So if we had the x values 5, 10, 15, 20, 25, 30, and if we had the y values, I'm just going to jump up here, 26, 28, 30, 32, 34, 36. So over 15 up 30, over 20 up 32, over 25 up 34. You notice for every x value we go over 1, but the y values we drop down 2. So we could sort of do the same thing and go back 1, down 2, and back 1, down 2. If it's a little hard to tell on your graph, we could back it up and go, okay, take off 5 here, 28 here, 5 here, 26 here, 5 here, 24 here. So we would get a y-intercept of 24. We could also use the point slope form that says y minus a y value, and we can just pick a y value, equals m times x minus the x value, which would give us y minus 30 equals, now when we distribute that we would get 2/5 x minus 30 over 5, which would be y minus 30 equals 2/5 times x minus 6. To get y on the side by itself, we're going to add 30 to both sides, so we get y equals 2/5 x plus 24. So we've sort of got three different options to find the y-intercept. Now I did y equals, but remember we're supposed to be finding a linear function f, so let's rewrite that as f of x equals 2/5 x plus 24. For this example, we're just supposed to graph. We can do a couple of things. We can do our table like we did in the earlier topics and plug points, or we can look at it and say, okay, the number in front of x is the slope, so the slope is 2. The number at the end is your y-intercept, which is -3. To graph that, we start with the y-intercept is -3. We put that point on the graph. The slope of 2 is the same as 2 over 1, which means every time we rise 2, we run 1. We rise 2, we run 1, which gives us our 3 points we need to graph a line, which if you check it, this ordered pair right here is where x is 1. If we plug in x is 1, we would get 2 times 1 minus 3, which is 2 minus 3, which is -1, which would give us the ordered pair 1, -1. Now for this example, when we graph the linear function, we're going to use our calculator. Remember how we graphed lines earlier? We're going to do the same thing here. We're just going to go to y equals, and for the function 2x minus 3, we're going to enter that as y equals 2x minus 3. Well, let's go ahead and hit zoom 6 to square our window up. So there is our linear function. Remember, like we said earlier, in order to transfer this to your graph paper, you might want to look to second table and pull off the ordered pairs. But remember, we know that the y-intercept is -3. And we know also that the ordered pair 1, -1 is on there. So that's enough points to graph that linear function. Let's do another one. So let's go to y equals. We'll clear out the function that was there. Because we have a fraction, let's put it in parentheses. So we get -3 divided by 2, close the parenthesis, times x. Now let's think about what this graph is going to look like. There is no number out here, which means the y-intercept is going to be 0. So it should cross the y-axis at 0, which it does. The slope is negative, which means it should go down as it goes from left to right, which it does. And the slope is 3 over 2, which means every time we go down 3, we should go over 2. So to get some points in order to graph it, we can go second table. So 0, 0 is on the line. Also, I'm just going to come down to this next pretty point, over 2, down 3. That way I'm not having to graph fractions. So that's what that line would look like. For the linear function f of x equals 20 minus 10x, same thing. Let's just sort of guess what it's going to look like. The number that doesn't have the x, that is our y-intercept. So y-intercept is 20. And the slope, which is m or a, is negative 10. So if we were going to graph it, the y-intercept would be 20. So I'm going to go 5, 10, 15, 20 way up here. Slope is negative 10, which if you think about it as being negative 10 over 1, that means you go down 10 every time you go over 1. So our graph is going to look like this. Let's check it. Y equals 20 minus 10x. Graph. Now remember, we're on our normal zoom screen, so what we can do is we can go up here to window. We can leave the x's from negative 10 to 10, so we could change the y min to negative 20 and change the y max to positive 20. When we press graph, then we get the line that looks like what we did on our graph paper. Okay, for this example, we're going to read a graph. The graph of f shows the number of gallons of gas in Jake's Jeep after X days. Estimate the initial and final number of gallons in the tank. So the initial value is right here, so the initial value would be 12 gallons. The final number of gallons in the tank, so over here at the end of day 7, it looks like we are at, well, notice it's not exactly 16, so let's say we'll estimate it to be 15 gallons. B part says, when did the number of gallons remain constant? Well, you see over on the graph how it did not go up and down between days 3 and 4. So the number of gallons remained constant between days 3 and 4. C part says, approximate f of 1 and f of 3. Well, f of 1 means the y value when x is 1, which means on day 1, it looks like this ordered pair up here is 116. So f of 1 is 16. F of 3 would be this ordered pair right here. So if x is 3, the y value would be 8. And then the last question says, at what rate was gas being used between days 1 and 3 inclusive? So day 1 was the ordered pair 116. Day 3 was the ordered pair 38. So the rate at which it was being used is basically the slope, which would be the y2 minus y1, so 8 minus 16, divided by x2 minus x1, which would give us negative 8 over 2, which is negative 4, which basically means we're using gas at the rate of 4 gallons per day. Now let's look at the graph for a second. We said the initial amount was 12 gallons of gas. Because it went up here, that looks like we went and added 4 more gallons of gas. And then we lost gas at a rate of 4 gallons per day here. Between days 3 and 4, it stayed constant, which means the Jeep was probably parked. Before the next day, we're back at 20, which means we probably went and filled our gas up at the station. And then on the next day, we used 4 gallons. And then on the next day, we only used 1 gallon. Objective 2 is modeling with a linear function. To model a quantity that is changing at a constant rate with a linear function f, the following may be used. F of x is equal to the constant rate of change, or our slope, or m or a, plus the initial amount. The constant rate of change corresponds to the slope of the graph of f, and the initial amount corresponds to the y-intercept. Here's an example. Marty's T-shirt and jacket company is to produce a new line of jackets with an embroidery of a Great Pyrenees dog on the front. There are fixed costs of $640 to set up for production and the variable cost of $39 per jacket. Write an equation that can be used to determine the total cost, C of X, encountered by Marty's company in producing X jackets. Our function is C of X equals the rate per jacket is $39, so it's 39 times the number of jackets plus the initial setup cost of $640. This is a function we could use to calculate the cost of any number of jackets. Another example. The table shows the number of students in millions attending a public school K through 8 for selected years. Let X be the number of years since 1997. So when we set up our table, what we want to do, and we're just basically shifting our graph back so that if we were doing a big graph, we wouldn't have to start it with 1997. We could start it back at 0. So what we're going to do is we're going to call this year 0. We're going to call this year 1, this year 2, 3, and 4. And that way we're not going to have to worry with those really large numbers. So A is your slope. So the first thing we're going to find out is what was the increase or the rate of change every year. Well, the years increased by 1 every year. The number of students, we notice this increased by 0.2. This increased by 0.2. This increased by 0.2. So our rate of change every year, so our slope is going to be 0.2. Our y-intercept is the value when x is 0. So in this case, it's going to be 33.1. So our function is going to be 0.2x plus 33.1, and this is a formula used to calculate the number of students attending a public school for any given year. And B part says find f of x. Well, we just did it, so f of x is 0.2x plus 33.1. The next part says to graph it and interpret the slope. Well, to graph it, let's just go back up here to the top. Because we did our zeros, so our first point, it would be 33.1, and then it increased 0.2 every year, barely going to increase very slightly every year. So it's almost a flat line, but there is a slight increase. Now interpret the slope. The slope was 0.2, which means every year the attendance increased by 0.2 every year. And then D part says predict the enrollment in the year 2005. Well, because we're dealing with the number of years since 1997, the first thing we're going to find out is how many years after 1997 is 2005. That would be 8. So 8 is the number we're going to plug into our function. So f of 8 is 0.2 times 8 plus 33.1. Well, 0.2 times 8 is 1.6 plus 33.1 would give us 34.7. So in the year 2005, we would predict an enrollment of 34.7 million students. Objective 3, linear regression. When a linear function is used to approximate data, it is called linear regression. We are going to use the calculator to get the line of best fit by using a method called the least squares method. This method minimizes the sum of the squares of the distances from the data points to the line. When we do this, we're going to talk about the correlation coefficient. This is denoted by R and is a measure of how closely the model matches the data. If R is equal to 1, if the correlation coefficient is 1, that means that there is an exact linear fit and the data matches that formula. The line passes through all the data points and has a positive slope. If R is equal to -1, there is an exact linear fit, as you can see in the picture. The line passes through all the data points, but this time the line has a negative slope. The correlation coefficient must be between 1 and -1. So if it's between 0 and 1, that means there is a positive correlation. As the x values increase, so do the y values. So the slope is a positive number, but the fit is not exact. Notice you've got a few points that are off of the line. As a note, the closer r is to 1, the more of a fit there is. If r is between -1 and 0, then we say there is negative correlation. You notice just like negative slope, the lines go down. As the x values increase, the y values decrease. And again, the fit is not exact because you have points that are not on the line. As a note again, the closer r is to -1, the more of a fit there is. If r is 0, there is no correlation at all. The points are just sort of randomly thrown in there. The data has no tendency towards being linear, and a regression line predicts poorly. That means it's not a good model. Again, as a note, the closer r is to 0, the less fit there is. Okay, let's do an example of the linear regression. The paired data above consists of the test score of 6 randomly selected students and the number of hours they studied for a test. By using linear regression, find a function where x is the number of hours studied and y is the score on the test. Use this function to predict the score on the test of a student who studies 8 hours. Round to the nearest tenth. Notice up here, it's not an exact linear fit because the numbers sort of jump all over the place. To do this on your calculator, we are going to enter the values just like we did in topic 1.1 or 1.2. We're going to go into Stat, and the first thing we want to do is edit. So we're going to select Edit, and we are going to enter the x values in L1, so that's going to be 5, 10, 4, 6, 10, and 9. Then we're going to enter the y values, 64, 86, 69, 86, 59, and an 87. This time what we're going to do is we're going to go back to Stat, we're going to slide to Calculate, but we are going to go here to option number 4, which was the linear regression. So when we choose that, we're going to press Enter. Notice it gives us our formula y equals ax plus b. So from our calculator we know that a is 1.066 and b is 67.35. Then it says to identify the correlation coefficient. Well, that is r. And notice on our calculator right now it's not on there. And if you're using the calculators in the lab, they're probably not on there either. So this is how you fix your calculator to get to r. First thing you're going to do is you're going to go to Second Catalog, which is second 0, and you are going to scroll all the way down until you get to the D's. You are looking for Diagnostics, and you want to turn the Diagnostics on. So you press Enter to select it, then you press Enter to turn it on. Now when you go to Stat Calc number 4 Linear Regression, notice now it gives you the R. So the R is 0.224. Now remember what we said, the closer it is to 1, the more linear of a fit it is. This one is not a very good fit, which basically says that the number of hours that the students are working does not really give you a good fit as to the score they're going to make on their test. C part says, is this line a good fit for the data? Because R is closer to 0 than 1, then I would say no, this is probably not a good fit for the data. Now let's go back. We didn't write it down. We identified A and B, but our function, our line of best fit would be 1.066x plus 67.35. Then D part says, use this function to estimate the score for someone who studies 8 hours. Well, that means we're going to go into our function. Everywhere we had an x, we're going to plug in 8. So we get 1.066 times 8 plus 67.35. This is probably one that we would want to use our calculator on. So we would get 1.066 times 8 plus 67.35, and that would give us a value of 75.878, which says 75.878, or an average score of 76, is what we might expect for someone who studies 8 hours. You are now ready to do the homework for Module 3, Topic 3.1 in my Math Lab.